In this video, I'm going to go through shuttles, which are important in biological chemistry because they move around the byproducts of metabolic pathways. And the purpose of going through them is to hopefully help answer this question. Why is glycolysis sometimes written to produce 30 ATP and other times 32 ATP? Well, it depends on where glycolysis is occurring in the body. In skeletal muscle, glycolysis will produce 30 ATP molecules because of the presence of the Glycerol-3-Phosphate shuttle. Because of how the shuttle works, every NADH is worth 1.5 ATP. However, in the liver, glycolysis will produce 32 ATP molecules because of the presence of the Malate-Aspartate shuttle. And because of the shuttle, every NADH is worth 2.5 ATP, more than what the NADH is worth in skeletal muscle. So hopefully after going through the shuttles, that will make sense and you'll understand why there's less ATP produced in the muscle as opposed to the liver. So in the muscle, we have the Glycerol-3-Phosphate shuttle. We've got glucose going through glycolysis to produce pyruvate. And we've got this step here of where we've got the two isomers being produced, glyceraldehyde-3-phosphate and dihydroxyacetone phosphate. Glyceraldehyde-3-phosphate will continue through, but dihydroxyacetone phosphate can be converted to glycerol-3-phosphate, hence the name of the shuttle, the Glycerol-3-Phosphate shuttle. And the enzyme that catalyzes this reaction is glycerol-3-phosphate dehydrogenase. So we've got a dehydrogenase there, and this is going to involve an NADH or an NAD in some way, and here it is. We've got an NADH becoming an NAD. It's the opposite direction to this side, where in glycolysis we have an NAD becoming an NADH. And that's because the products of this reaction feed into the reactants of this reaction and vice versa. The products of this reaction feed into the reactants of this reaction. So it's a dynamic process. As well, with this enzyme, in the mitochondria, it'll produce an FADH. An FAD will become an FADH. And ultimately, this will produce 1.5 ATP, which will go into the electron transport chain. It produces 1.5 ATP and is less than the Malate-Aspartate shuttle because it skips complex 1 of the electron transport chain. So I'll repeat that one. It skips complex 1 of the electron transport chain and it is worth less, therefore, ultimately, than the NADH, which will get transported into the mitochondria and the liver, which we'll go through in a second. So ultimately, this less amount of ATP, because we've skipped complex 1 and we skip some of the protons that are going into the inner mitochondrial membrane space, which are then ultimately used to produce ATP. We've got less protons, less ATP, and ultimately, glycolysis in the muscle will produce 30 ATP. So that's what's happening in the muscle. So if we just move this out of the way and we get out our Malate-Aspartate shuttle. It's quite a dynamic shuttle, as you can see with all the arrows, but don't be alarmed, we're going to go through it. So we've got aspartate becoming oxaloacetate. I'm going to start there. It's a cycle, you could start anywhere, but I'm just choosing to start here. So the enzyme here is aspartate aminotransferase, and here we have a alpha-ketoglutarate, a bit of a mouthful, becoming glutamate. So it's an aminotransferase, which is a transaminase enzyme, a type of transaminase. So they catalyze transamination reactions, which transfer an amino group to a keto acid to form new amino acids. So that's what's happening in this dynamic process, and that's why it looks a bit different to some of the other reactions you might have seen in biological chemistry. There's a transfer of amino groups going on between these 4 chemicals. So we've got a transfer there. So we've got oxaloacetate then becoming malate, as you can see, and this enzyme up here is malate dehydrogenase. We've got an NADH becoming an NAD, pretty straightforward, and then we've got a malate which can go straight into the mitochondria by the malate alpha-ketoglutarate antiporter. And this malate can then go back and become oxaloacetate. And this is the key step. So instead of an NADH becoming an NAD, on this side we have an NAD becoming an NADH. Now we've got NADH inside the mitochondria, and this will produce 2.5 ATP in the electron transport chain. This is because we're not skipping complex 1, we're going straight to complex 1 where there's an NADH. Might be worth looking at your electron transport chain as you watch this video, so you can see that we've got that NADH for complex 1, we don't have to skip it, and we can go straight through and make the maximum amount of ATP, and therefore the NADH is worth 2.5 ATP, as opposed to what we saw before in the muscle where we have an FADH which gets into the mitochondria, which skips complex 1, and we go into complex 2 because that's where that FADH is used. So that's what's going on there. And ultimately, glycolysis here, in this case, will produce 32 ATP because we've got 2.5 ATP here as opposed to the 1.5 that we had in the muscle. Just continuing the cycle on though, we've done the most important part, but just to complete it, oxaloacetate can become aspartate. Again, it mirrors the other side, aspartate aminotransferase here. And the glutamate is also has an arrow to alpha-ketoglutarate here because we've got that transamination reaction where an amino group is transferred to a keto acid. So it's a pretty special type of reaction. And that is the Malate-Aspartate Shuttle complete. Aside from, here I'll just label this one the glutamate aspartate transporter, because as you can see here, it can transport glutamate and aspartate, and up here we had malate alpha-ketoglutarate because it can transport malate, and here this alpha-ketoglutarate can join in up here. I'll just direct that better. And that's what's going on there. And just something that I forgot to mention earlier, just the key here, that's the outer mitochondrial membrane and the inner mitochondrial membrane space. So ultimately, in the Glycerol-3-Phosphate shuttle, we get an FADH in the inner mitochondrial membrane space, which ultimately produces less ATP in the electron transport chain, as opposed to the Malate-Aspartate shuttle, where you can see here, we have an NADH, which goes straight to complex 1 of the electron transport chain, and we get more ATP, 2.5 ATP. And that's what you need to know about shuttles.